How about c equals 2? Well, here the line elements will be slanty. They'll have slope 2. So pretty slanty up. And I can see for c equals 3 in the same way. They're going to be even more slantier up. And here they're going to be even more slanty down. This is not very scientific terminology or mathematical, but you get the idea. Okay, so there's our quick version of the direction field. All we have to do is put in some integral curves now. Well, looks like it's doing this. It gets less slanty. Here it levels out, has slope 0. And now in this part of the plane, the slope seems to be rising, so it must do something like that. This guy must do something like this. I'm a little doubtful of what I should be doing here. How about going from the other side? Well, it rises, gets a little... Should it cross this? What should I do? Well, there's one integral curve which is easy to see. It's this one. This line is both an isocline and an integral curve. It's everything. Except drawable. So, okay, you understand this is the same line. It's both orange and pink at the same time, but I don't know what combination color that would make. It doesn't look like a line, but you know, be sympathetic. Now the question is, what's happening in this corridor? In the corridor, that's not a mathematical word either, between the isoclines for, well, what are they? They're the isocline for c equals 2 and c equals 0. How does that corridor look? Well, it's something like this. Over here, the lines are all look like that, and here they all look like this. The slope is 2. And a hapless solution gets in there. What's it to do? Well, do you see that if a solution gets in that corridor, an integral curve gets in that corridor, no escape is possible. It's like a lobster trap. You know, the lobster can walk in, but it cannot walk out because the things are always going in. How could it escape? Well, it would have to double back somehow, and remember, to escape, it has to be, to escape on the left side, it must be going horizontally. But how could it do that without doubling back first and having the wrong slope? The slope of everything in this corridor is positive, and to double back and escape, it would at some point have to have negative slope. It can't do that. Well, could it escape on the right-hand side? No, because at the moment when it wants to cross, it will have to have a slope less than this line, but all these spiky guys are pointing the other. It can't escape that way either. So no escape is possible. It has to continue on there. But more than that is true. So solution can't escape. Once it's in there, it can't escape. It's like those, what do they call those plants? I forget. Pitcher plants. Pitcher plants. You know, all the hairs are going down, so it looks like that. And so when the poor little insect falls in, it could climb up the walls, except that all the hairs are going the wrong direction and it can't get over them. Well, think of it that way. This poor trapped solution. Well, so it does what it has to do. Now, there's more to it than that, and because there are two principles involved here that you should know that help a lot in drawing these pictures. Principle number one is that two integral curves cannot cross at an angle. Two integral curves can't cross. I mean by crossing at an angle like that. I'll indicate what I mean by a picture like that. Now, why not? This is an important principle. Let's put that up in, at least in a white box. They can't cross because if two integral curves are trying to cross, well, one will look like this, because it's an integral curve because it has this slope, and the other integral curve has this slope, and now they fight with each other. What is the true slope at that point? Well, the direction field only allows you to have one slope. If there's a line element at that point, it has a definite slope, and therefore it cannot have both this slope and that one. It's as simple as that. So you can't, the reason is you can't have two slopes. The direction field doesn't allow it. Well, that's a big, big help, because if I know here's an integral curve, and if I know that none of these other pink integral curves are allowed to cross it, how else can I do? Well, they can't escape, they can't cross. It's sort of clear that they must get closer and closer to it. You know, I'd have to work a little to justify that, but I think nobody would have any doubt of it who did a little experimentation. In other words, all these curves join that little tube and get closer and closer to this line y equals x. And therefore, without solving the differential equation, it's clear that all of these solutions, how do they behave? As x goes to infinity, they become asymptotic to, they become closer and closer to the solution x. Is x a solution? Yeah, because it's an y equals x is an integral curve. Is x a solution? Yeah, because if I plug in y equals x, I get what? On the right-hand side, I get 1, and on the left-hand side, I get 1. 1 equals 1. So this is a solution. Let's indicate that it's a solution. So analytically, we've discovered an analytic solution to the differential equation, namely y equals x, just by this geometric process. Now, there's one more principle like that, which is less obvious, but you do have to know it. And so they're not allowed to cross, that's clear. But it's much, 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 much less obvious that two integral curves cannot touch. That is, they cannot even be tangent. Two integral curves cannot be tangent. I'll indicate that by the word touch, which is what a lot of people say.